Hello and welcome to Group 9 Senior Design Presentation. Our team today would like to take this opportunity to discuss how our project began, where it is at, and our next steps. Our project started off as a complaint from a team member. Bears were often getting into his trash bins and he wanted to find a way to stop this from happening. We then worked together to create a solution that will be discussed in detail as we progress through this presentation. As the Florida bear population continues to grow, the more trash bins are being rummaged through. There are ways to deter bears and other animals from doing this without causing harm to them, creating a safer environment for both humans and bears. Our team, who is working together to design and build a solution, is made up of Austin Woodleaf, Electrical Engineering, Levi Zima, Electrical Engineering, Philip Marcel, Electrical Engineering, and Bruinas Gonzalez Ramirez, Computer Engineering.
One of our main motivations is to allow the device to deter bears and other pests from getting into customers' property, specifically their trash cans. Aside from the trash cans, we hope that this deterrence will also aid in the prevention of damage to consumers' property due to animals trying to gain access to the trash cans. This damage could include, but is not limited to, damage to the trash can the device is attached to, the area surrounding the trash cans, the consumer's yard, driveway, and vehicles. There are likely more things that could be damaged by unintended visitors, but we feel this list is sufficient enough to illustrate the need for our product. Secondary motivation, or rather what we hope will be a secondary effect of the consumer utilizing our device, is to prevent further visits from these nuisances. We expect that due to the device being attached directly to the trash can, it will further de-incentivize animals from interacting with the can at all. We would like to make note that we are not professionals when it comes to animal behaviors, so this outcome is not guaranteed.
While traditional solutions rely on locking trash bins, we offer a comprehensive approach to bear deterrence. Our system combines a user-friendly mobile app with effective deterrent methods. Strategically placed LEDs emit bear-repelling lights, while high-quality speakers produce unpleasant sounds for bears. The multisensory approach actively discourages bear encounters.
While we are determined to achieve our goal, we would also like to focus our device's usability towards pests of all sizes. This list includes animals like bears, raccoons, possums, stray cats, and similar creatures. Any pests that want to get into whatever our device is attached to is something that will need to be deterred. As I'm sure many of you are aware, if an animal can get into a container, whether it is open or not, they will try until they eventually succeed. Most of us probably have experience with pets attempting to investigate a box or something simply because of their innate curiosity. However, while pests do exhibit similar propensities, they are primarily trying to consume whatever they can, whether it is a part of their natural diet from the roadside or even your trash. Due to this fact, we are determined to create a deterrent that is focused primarily on scaring away pests rather than attempting to incapacitate them.
We will now go over the requirement specifications. First, the system must be equipped with a minimum of one sensor, enabling it to gather input and detect potential tampering events. It is crucial for the system to achieve at least 90% accuracy in notifying the user of such events based on sensory input. Secondly, the device itself should exhibit a low power draw. The design consideration enables the device to maintain usability for an extended period of time with a minimum requirement of 1 month. In terms of physical dimensions, portability is a huge factor. The device should be as compact as possible with dimensions not exceeding 6 inches in length, 4 inches in width, and 3 inches in height. Furthermore, the system should offer seamless integration with the mobile application. Upon triggering the device through the mobile app, it should respond with a maximum time frame of 20 seconds. The user should then receive a timely notification within 60 seconds alerting them of a triggered event. In conclusion, our system aims to meet these requirements, ensuring reliable sensor input, low power consumption, extended usability, accurate tampering event notifications, portability, swift response to mobile triggers, and timely notifications to users.
Our work distribution really came together quite naturally. We were always willing to help each other out when others were going through rough patches or just busy with work and life. And really, I couldn't give that up for anything else. I'm very thankful for this group that we have. And if we had to quantify it, the work distributions are as follows on this slide. But really, we all always helped out when needed.
Over the course of this presentation, we will go more in depth with what those responsibilities entail. But the broad breakdown of our members' responsibilities can be seen on this slide here. As was discussed previously, the work distribution has Levi and Phil focusing primarily on aspects of the hardware design, while B and Austin are focusing on different aspects of the software. This breakdown is not fixed, as we may at one point need to focus on one component or aspect of the project, as it is impeding progress of the project as a whole. But it is an accurate representation of what everyone's primary responsibilities are. Here is a breakdown of our primary components and how they will be interacting with one another. While this is an overview, we will be going more in depth with our specific component choices over the coming slides.
The Bluetooth module selected for this project utilizes the ST Blue Energy 1. It's capable of working in conjunction with LoRa technology, as well as the chip is extremely small and has very low power consumption, which makes it perfect for an application like this, saying as how the size of the device needs to be relatively small since it's being mounted on the side of a storage container. The LoRa chip being used for this project is the SX1262, which is Semtech's solution for an embedded LoRa chip. The antennas being considered for this project were the helical and monopole antennas. We decided to go with helical antennas due to their small form factor while still being resonant at the frequencies required for this project.
For a thermistor, we will be ordering an 0603 size part from Mouser Electronics, part number ending in J60RB, manufactured by Murata Electronics. This thermistor is ideal for our application because they are 10 cents per unit and we can order quantities of one. We have ordered 5 thermistors for our project so that we can have ample replacements should anything go wrong soldering this small part on our mounted device. The small form factor allows us to keep our device size small so that we can mount underneath the trash can handle. As you can see in the bottom right corner, the resistance to temperature graph shows we should expect around a 5 kilo ohm resistance in the operating temperatures of Florida heat. We will be able to take this resistance and throughout integration and test, figure out exactly which temperature is in the ambient air surrounding our device. Here you can see the temperature sensor schematic that we will be using in conjunction with the thermistor from the previous slide. This simple circuit will allow us to take in the ambient temperature and relate that to an apparent resistance value. From there, we can extrapolate what the actual ambient temperature is outside. For the sound deterrent portion of our mounted anti-tampering device, we will be using a piezo buzzer. This buzzer is capable of producing 78 decibel noise that will be efficient in scaring the very sensitive hearing bears away from our trash. This particular device has a through-hole style mounting, which will allow us to create an even stronger binding to our PCB and subsequently to our mounted trash can system. As a visual deterrent, we will use red and white LEDs, flashing on and off in alternating colors to hopefully startle away the bears from our trash without committing any long-term harm to them. This system is fairly straightforward and can be accomplished with our knowledge of embedded systems coding.
An accelerometer was chosen as the motion sensor due to its ability to very accurately detect if an object is being moved. This specific accelerometer was chosen due to its ability to sense in 3 different axes with high sensitivity and resistance to temperature change. It was also chosen due to our previous experience in working with analog devices inside microcontrollers utilizing A to D inputs.
For our accelerometer, we will be using the 3-axis sensor ADXL326. This accelerometer has 3 separate outputs for each axis, X, Y, and Z. This will allow us to construct our project with the capability of capturing data from all three axes simultaneously. It is also worth mentioning that this accelerometer is incredibly rated for high temperatures, which will make it perfect for withstanding the Florida heat.
This MCU was chosen due to being versatile in its method of transmission, as well as its extra options for more possibilities later. The MCU can communicate via SPI, I2C, USART, which stands for Universal Synchronous Asynchronous Receiver Transmitter, and LPUART, which stands for Low Power Universal Asynchronous Receiver Transmitter. The chip also comes with 3 separate clock sources for the system clock, with the fastest source being capable of running at 48 MHz. Some peripherals also have their own independent clock source, such as the ADC, I2C, and SPI. Speaking of the ADC, it operates natively at a 12-bit resolution. This resolution can also be increased to 16-bit via hardware oversampling. This MCU also comes equipped with a temperature sensor and multiple timers. There are 2 timers we would like to highlight that are designated as low-power timers.
Here is an image of the LoRa BGA sensor board. This schematic has the accelerometer on the left side connected to 3 different pins for the 3 outputs of the analog sensor. It has the LEDs as well as the piezo, and also the temperature sensor on the upper center of the schematic. Each of these are connected to their own specific pins and will work in conjunction with inputs, different input pins and outputs. This hub schematic shows the LoRa module on the upper portion and the Bluetooth module on the lower portion, as well as their respective programming headers and battery connection as well. And as can be seen in the schematic, on the left side, each module has its own specific antenna, which is very important due to the differences in frequency between LoRa and Bluetooth. This layout was done utilizing a 2-layer board, which has a trace plane on the top of the board and a ground plane on the bottom of the board. Each of the power lines were routed individually, and the traces that were prioritized were for the antenna and sensors as to limit noise and improve performance. The device was also made as small as possible while still maintaining the ability to utilize the 2 AA batteries mounted on the bottom of the board. This layout was done similarly to the previous one, prioritizing the communication between the LoRa and Bluetooth modules as well as the antenna placement on the board.
We will be modeling our enclosure off of the Osceola County standard Florida trash can. This trash can has a convenient slot that is insulated from above in the very front of the trash can. As you can see in the top left zoomed in picture, there's ample space for us to fit our small low profile device underneath this flap of the trash can. From there, we can add extra weatherproofing underneath while still maintaining an open air to get relatively accurate temperature.
In comparison to other available options such as Android Studio for Android development and React Native for cross-platform development, SwiftUI stands out for its seamless integration with iOS ecosystems. While Android Studio is well suited for team environments and offers Firebase and cloud integration, SwiftUI is specifically optimized for iOS devices, ensuring a smooth and consistent user experience across Apple devices. React Native, on the other hand, excels in its ability to create reusable components and offers an open source platform with hot reload functionality. However, our decision to choose SwiftUI was driven by the project's focus on iOS development and the need for deep integration with Apple's ecosystem. SwiftUI's native approach and strong compatibility with iOS features, along with its intuitive syntax and rapid development capabilities, made it an ideal choice for a mobile application.
The project is intended to be capable of measuring movement along the X, Y, and Z axes. This will be accomplished using the ADC of our chosen MCU, and a more detailed explanation will be given in a few minutes. The temperature measurement is measured via a dedicated pin connection to our MCU. This was done as the temperature sensor is not a separate component but rather a set of resistors set up in a voltage divider. The device will capture data from the sensors and compare it all directly on the main device. This will reduce the amount of data that is being sent to the user and will allow the transmission times to the user to be much smaller. Finally, the main device will be capable of enabling or disabling the connected deterrents. This feature can be utilized at the user's discretion. The device-to-device communication will be done through the use of Bluetooth. The modules we intend on utilizing will be capable of LoRa, the long-range communication technology we previously mentioned. The main device will be located on the user's trash can. This device will monitor for disturbances based on readings from the attached sensors. Once a disturbance is registered, the trash can device will begin to communicate with the hub device. This device will receive the transmitted signal from the main device. Once received, the hub device will then send a notification to the user via Bluetooth when they are within range of the device. There are alternative methods for communicating to the user that their trash can has been tampered with, but they will be discussed in a later section of this presentation.
The approach to device communication differs between the mobile app and the embedded system that sends and receives information. Primarily, data transmission from the hardware to the mobile app occurs via Bluetooth. By leveraging Apple's documentation, we have successfully identified a method for transferring data between Bluetooth low-energy devices. The mobile application assumes the role of a Bluetooth central by using classes such as CB characteristic and central manager. Communication with the Firebase database is exclusively achievable through the mobile phone and the website. Given the project's context, we anticipate user access through the mobile app, enabling them to retrieve current and past notifications exclusively through the mobile application.
The accelerometer on the trash can device will detect movement along one or more likely multiple axes. This data will be captured by the MCU and compared with our predetermined threshold values using the ADC, also located inside of the MCU. This comparison will then determine if the user will be notified if at or exceeding the threshold value. The device will begin the process of transmitting to the user. Once the notification condition is met, the trash can device will begin transmitting a signal to the hub device, which will likely be located much closer to the user. This device will then receive the signal and transmit a notification to the user via the mobile application. We will talk more in depth about the application in the coming slides. Moreover, from the application, the user has the ability to respond to the notification. Their response is then transmitted back to the trash can device where it is interpreted. The use case diagram illustrates the hardware's various interactions with other system components and the end user. The end user is primarily responsible for logging in, receiving notifications, and triggering the deterrent. These tasks are facilitated by the hardware's role in data transfer between components and the mobile application, enabling seamless user engagement.
The mobile application currently consists of 3 primary screens. However, it is anticipated that the application will be expanded to incorporate 4 main views. These views include a login screen to authenticate user access, a comprehensive list displaying current and past notifications of triggers, a dedicated view so the user can trigger the deterrent system, and finally, each view will provide the user with an option to navigate back to the previous screens, ensuring a seamless user experience. Our app will have 4 main features. The first one being that we provide secure login authentication, ensuring user data remains protected. The second one being that our app will excel in sending timely and accurate notifications, keeping users informed. We would also offer comprehensive notification tracking, enabling users to monitor event history. Furthermore, our app is expected to have seamless integration with Firebase, which allows for efficient data management. As a unique stretch goal, users should be able to trigger the deterrent system directly from the app.
We would like to thank RF Laboratories for all of their help and donations to our project. As you can see in the table below, they greatly help to alleviate the costs of our overall project design, donating many of the components necessary to our cause.
The primary hardware design challenges that we face so far mainly have to do with routing and the footprints of certain parts. The routes for the antenna design and orientation were most critical, and the entire board layout had to be revolved around the placement of those devices, as well as how small the pads are for the surface mount accelerometer.
During the initial brainstorm phase of our mobile application, we faced challenges accessing Xcode for SwiftUI development. We resolved this by obtaining an older MacBook. The team quickly adapted to SwiftUI syntax thanks to its similarity to Objective-C. Setting up Firebase and Xcode required multiple restarts, but was eventually successful. While hardware-related, challenges have been minimal, selecting the appropriate environment IDE and addressing syntax considerations remain ongoing challenges.
Given the size constraints of our project and our desire to be able to assemble it by hand, we have decided to go with all 0603 standard part sizes for capacitors and resistors on our mounted and hub PCB devices.
Now we will be going over some stretch goals. Initially, we considered allowing users to individually enable different deterrence methods for flexibility, battery efficiency, and usability. We also explored the idea of sending emails converted to text for broader notification options. However, we prioritized focusing on the device's core functions. Additionally, we have the capability to measure the battery level and notify users when it reaches critical levels.
The two primary components for this project are the ST Bluetooth Blue Energy 1 chip and the ST LoRa chip, which works in conjunction with Semtech to provide a LoRa solution all in one device.